All right, let's get started. Welcome to Robotics 311, Lecture 3. Today, we're going to kind of keep going through this design framework that we're learning. We're going to just discuss briefly the review of motors and transmissions that we've learned, and we're going to begin like planar modeling of a ballbot. So this is kind of step one to understanding the input requirements for our design pipeline. Ideally, if we get all the way through it, we'll get to a MATLAB example where I'll kind of walk through the exact steps and go through kind of calculating the current and voltage that we need for the system. And then you'll have on your homework, which I'll post today, and I'll push the due date back a little bit, you'll have on your homework an example problem where you'll kind of solve this using the same pipeline. Currently, I have the homework is going to be due a few days after it's posted to be due on the syllabus since I didn't post it earlier. Most of it is Basics 1 and Basics 2, so I think you guys are on that already. But I'll push the due date for homework 1 back a little bit. And then if it seems like since this class is new and the content is kind of intense, I want you guys to learn it, and homework is going to be part of that. I also know this class is going to have a lot of work associated with it, especially on the ballbot construction and building side. So just keep me posted on how much time the homework is taking you, if you feel like it's taking you too long, that kind of thing. Yeah.
Where is the homework posted?
It will be posted today on Canvas.
Okay.
There'll be
under an assignments tab or?
There'll be under assignments, that's where you'll upload it, and it'll be under the files tab.
Awesome, thank you.
Yeah. Okay. Microphone?
Yeah, this is your microphone. Sorry.
No worries. Okay. So tomorrow we're going to do Lab 2. Lab 2 is going to consist of building an image, which is basically the brains of your Raspberry Pi. And we're going to have a kind of a process we're going to go through together to build it. What you'll need is your laptops. You'll also need a GitHub account. So if you have one, good, we'll need you to use it. If you don't have one, you'll need to create one. Yeah.
I think we did a lot of that stuff last week as far as the building, the GitHub and everything. Are we just continuing that? Oh wait, that was 3:30. Never mind. Just
we did that in this class. Okay, yeah, so you're going to create a GitHub account. So if you have one, you create it for 3:30, great. What we're going to end up doing is forking a repository that we built custom for this class, using that repository to build the image, and that's going to be tomorrow's lab. So, GitHub account. Okay. So we've begun this class by learning this framework, which is kind of how to spec a robot when we're thinking about the actuation system, so the motors and transmissions. Those things are especially important, especially for motors or for robots that move in the environment and carry their power sources. They want to be lightweight and efficient, so they're kind of assessing the actuator and the transmission ratio has a lot to do with that. So we've begun this framework, learning how to model the required capabilities of a robot's actuation system. And this process is general, but we're going through it specifically in the case of a ballbot. But if you, in the future, you're doing some other task, this same process would be how you solve it. So you would need some description of the output mechanics, which you could either model like we're doing, or maybe you have that from a paper or another investigation. There might be other ways to get that, but the most common way is to model it, some version of what we're doing here. We want to use knowledge of our task requirements and selection of motor and transmission, which impact physical design and control. So we want to make some smart choices now that we're going to reap the benefits of when we're doing the physical design and control. And then we're talking about this framework. So at the end, I think you guys get this now, at the end we're getting a motor transmission ratio, which we assess based on current and voltage, the required torque speed, and the temperature increase of the windings. And if all of that checks out, then it's a feasible solution. So I'm going to do a little bit more on transmissions to make sure everyone's on the same page. We talked about modeling transmissions. We were modeling them this way, so we might have to an output velocity requirement and an output torque requirement, which we then go backwards through the transmission to find the input requirements on the motor side. The things that are important is we're going to scale velocity up. So the input's going to go much faster. That's really common, especially with motors because of the way they produce power. And the torque is going to go down. And we're also going to add that efficiency. So it's going to be divided by the torque will be divided by the transmission ratio and the efficiency. Common efficiencies are around 0.8 to 1. So we talked about transmission efficiency depends on type and stages. So type we talked about, we'll have a lecture on transmission types, but there's different ways to build transmissions, linkages, gears, belt drives, ball screws. They're all different ways of creating this relationship about scaling speed and torque. And then if we need a high transmission ratio. Oftentimes people stack multiple transmissions in a row. That's called a compound transmission. Then all the efficiencies get multiplied. You start to see a much lower efficiency. So typically we would try to avoid that. Transmission scale, torque and velocity. Inversely. So it scales speed up and torque down. Usually the input speed is much greater than the output speed. And usually the input torque is much less than the output torque. Anybody know of an example of a transmission ratio that's ratio is less than 1? Something you might see in a car or a certain setting in a car. I'm not 100% sure of this, so don't quote me on this, but I think this is correct. You guys have heard of overdrive? An overdrive gearing, which is like your top gear. That's usually an inverted transmission ratio. That happens when the car is moving fast. Okay, let's do a cartoon example. Okay, so here we're going to look at, this should say torque. So here, I'm going to plot in a sort of a shaded region a potential task. So let's say the input to this task exists somewhere in here. So if I were to look at the torque velocity requirements from the input of the motor, it might exist somewhere in this range. So let's say I want something like this. So if I add a transmission, I'll scale this. So I'm going to scale the velocity down and the torque up. What's that transmission ratio, approximately? Look at that and tell me. So this might be a task, which we might see as some curve where we look at the torque and speed of our input. It might exist somewhere here. So we have a motor that's running really fast and producing a little bit of torque. And then we want the output to scale the torque up and the speed down. So now our task, instead of existing in this shaded region, exists in this shaded region. What is that transmission ratio, approximately? Yeah, about 5 to 1. How'd you know that?
Just looking at the distance in the x-axis or the y-axis, like comparing the theta dot range. Comparing the two theta dot ranges or the two.
What are the two torque ranges? Yeah, so you basically said, okay, this is maybe 1/5 of that, and this is maybe 1/5 of this. So that gives us a transmission ratio of about 5 to 1. Everybody good on that? I think you should be able to look at this and identify the transmission ratio broadly, with ease. That would just show you that you have an accurate understanding, or the understanding we want in this class. So that's a little cartoon example. It would shift any sort of region that existed in torque speed would be scaled this way by any transmission ratio. This is how they work. Scaled torque and speed in this way. We're just looking at it in the torque speed plane right now. Cool? Okay. I want to talk a little further about this. So here, I've as a reminder, like phi is what's going to be the wheel angle, but we'll come back to that. But that's why you saw phi and phi dot and psi dot. Those are sort of the variables that'll come with the modeling, whereas theta is kind of the typical angular dimension used. So this dimension, or this slide, takes all of our conventions of other variables out and just calls them output and input, just to make sure everyone's like clear on exactly what's going on. So in this little example here, we have a motor, that's the input with some inertia Jm, driving a gear train with an output load. This we'll say is diameter d, this is maybe 3d, this is a transmission ratio of 3:1. And if we look at the equations that would tell us this transmission ratio, we can get it by any of these equations. So 3d over d, that's just the ratio of the diameters. N2 over N1, that could be the ratio of the number of teeth on the example. We could also do this theta dot input over theta dot output, torque dot output over, torque output over torque input. Note that, so if they scale inversely, if we're equating them here, the output and input are reversed when you look at theta dot and torque. Okay, so a question that I think you guys might be wondering when sometimes people ask me, and I think is very relevant to robotics, is how would an inertia on one side or the other affect the mechanics? So here we're going to talk about what does this inertia at the output feel like to the motor? Okay, we want to know how much does that motor have to work to move the mass around on the other end. Yeah.
I mean, if it's a positive one, wouldn't it feel harder? It needs to have, because it's increasing the torque.
That's true, but it's,
So it would be easier for the motor to.
yeah, well, so like it goes both ways. It depends on which side you're looking at. So like, that's why I'm really intentional right now and saying we're looking at the motor side. So if we look at the motor side, one way to wrap our heads around the effect of adding mass is to just look at kinetic energy and rearrange terms. So if we create the equation for kinetic energy, it's going to be 1/2 the inertia of the motor times theta input squared, plus 1/2 the inertia of the output times theta output squared, just total kinetic energy. And we also know that theta dot output is theta dot input over n. So now we can rearrange this. We can write it only in terms of theta dot input, which means now we only care about the motion of the input and how the inertia will feel for motion of the input on the motor side. So this is now written all in terms of the input, and if I collect those terms, I get this expression. Now I have 1/2 times some inertia value times theta dot input squared. So now we have just straight up kinetic energy, but we factored everything to be only about the motion of the input. What happened to the inertia of the load?
Gets divided by n squared.
Gets divided by n squared. So for a transmission ratio of something like 70, we're dividing that load inertia by a large number. So the inertia that we end up seeing kind of on the motor side when we're doing these analyses, the inertia that ends up coming mostly into play is the inertia of the motor itself. Because all the inertia of the output gets reduced by the transmission ratio squared. Now let's think about it the other way. What happens if you back drive the system, you take the output, I'm going to drive this output. Now I want to know, how does this inertia feel then? If I drive this output, so we know what would happen? Has anybody ever back driven an actuator? Like, can you recall doing that? What did it feel like?
It will be very heavy.
Really heavy. Yes. So what happens here? Everybody know? Like, so this relationship will get reversed. We put it in terms of the output. You know the answer?
Wouldn't the ratio instead of like 3 to 1 be 1 to 3? So the 1/3, it will flip the ratios and square will make the load inertia weight higher.
It will make the motor's inertia be way higher.
Oh.
So, but that's right. So because we're talking, we would be,
Sorry.
yeah, we would be rearranging these. It would make the motor's inertia field n squared heavier.
Yeah.
Or really n squared more rotational inertia, so more rotational mass. So this comes into play a lot in robotics. A lot of robots want to feel not like a robot. They want to feel compliant or maybe more like a human. So a lot of tools in robotics are aimed at reducing the transmission ratio for this. And this particular project, we don't necessarily care a ton about that. If people aren't interacting with the system, all it has to do is the tasks of the ballbot. But if you had humans involved, that would sort of come into play here. So, yeah, but
I was gonna say, wouldn't it be kind of like useful though for it to have, like to be able to make it hard to push the actuator where like let's say you're trying to hold a box down and someone tries pushing it down, wouldn't you want the transmission to lock its arms there because it wants to be there for a reason?
yeah, so that's a different concept, but a good point. So that concept, I think what you're saying is, well, maybe there are certain times where backdriving the system is not advantageous, and it would be more advantageous to have the system hold its position, sort of be locked without effort.
Yeah.
So there are types of transmissions that do that, which would be called non-backdrivable, where they can't run this direction, so physically impossible. So those exist and they are useful in many applications, but not typically it wouldn't be in our application, and you might not see it. It's less common.
What are the like, applications of having the backdrivable? Because like I can think of like non-backdrivable for like elevators or like arms and things like that. Like you wouldn't want it falling down once you stop applying power. What would be a case like, or even like driving like a rover, you wouldn't want somebody able to push it out of the way per se because it probably wants to be there for a reason.
Yeah.
So what would be a case where you want it to be backdrivable?
Yeah, good question. So what happens when you run a motor in negative power?
It would generate the power.
It generates energy. So if we're talking about robots, maybe we have to carry our power sources, we often want to use that energy. We want to regen to save this energy. If you use a non-backdrivable transmission, you cannot regenerate any energy.
Okay, so it's kind of like how Tesla does like with they do I think backdriving with their brakes, right?
Definitely,
So
yep.
that would be a case for it.
Yeah, that's when and for example, another case would be anything that involves compliant interaction. If you want the system to be compliant, it's going to have to be able to be backdriven.
Gotcha.
Yeah.
Is an example of that also like those cars that you would kind of like roll back to like wind up their like the little toy cars
Yeah.
that you could like pull back and then all of a sudden they use that to like
Yeah, that's backdriving for sure. Yeah, you're backdriving that.
I guess that's just like an advantageous one where you're using that kinetic energy.
Yeah, you need it. That's right. I think that's another good example. Those are cool actually, those little cars. I have a 2-year-old and a 5-year-old, so I play with these cars a lot. A lot of times what they do, if you play with these cars, and I don't know if you've seen the ones, but if you give it a push, it sort of drives for a long time. And like if you look at what those are doing, and you can hear them, what they are is just a small mass and a huge transmission ratio. So when you backdrive it, you're actually like spinning up this mass, and it holds some energy. And then when you let it go, it just runs that energy out. But it uses this reflected property to generate a ton of stored mechanical energy. But yeah, so this is something to know. This right here, we have a special word for that. We're going to call it equivalent or reflected inertia. So when mechanical properties go through a transmission, they get reflected. And that can be a reflection by n squared or a reflection by 1 over n squared. And it's this same rationale would apply to anything, any mechanical property on the input or output. So it's not just mass or rotational inertia, but if there was a spring here or a spring here, that would affect its constant. We would see the spring, if we were looking here and there's a spring here, we would see the stiffness divided by n squared, just like inertia. So this is something to put on your radar, something to know for actuation in robotics, but not something that's going to come to play a ton in this project. That's something I wanted to make sure you guys had seen. So I also have a little note here that says, Oops. How do I get that out of there?
In the top left, I think, next to the arrow.
This thing?
Oh wait, maybe not.
I think we're okay. Okay. So JL is reflected inertia on motor side. It should be JL over N squared. So JL over N squared is the reflected load inertia on the motor side. Okay, so I just want to make sure you guys saw that. So this kind of brings us kind of where we were last lecture, stacking a motor. We want to know which one is right. How do we know this? We do these analyses. We talked about these equations that govern brushed motor operation. I think you guys track voltage is sort of roughly proportional to speed, current is roughly proportional to torque. We have a circuit here with an applied voltage, a drop across the resistance, drop across the inductance, drop across back EMF. And that's going to equal that applied voltage. And we think of motors as a transformer. Only have one transformer constant. What is the name of that constant? Back EMF constant or the torque constant? They're the same. They have different units, but they're the same number. We talked about solving these equations, how we would do this if we define our outputs, our output mechanics. We would first solve the equation for current, and we would plug that equation in, numerically differentiate, solve for voltage. We talked about the linear nature of motor torque speed curves, where they have this slope, kt over r, kt squared over r, and that a diamond represents an applied voltage. So depending on that applied voltage and the torque being provided, it will sort of ride along these lines, where if you scale that voltage, that diamond grows or shrinks. We talked about salient properties of this curve, namely the stall torque, the no load speed, which are here and there. And then we talked for a minute about like power. And I kind of created a slide. I have this slide that was shown when we talked about positive and negative power, and I showed it for positive. I added the negative version of this slide, so that's what we're going to talk about next, just to make sure we're on the same page. So anytime voltage and current are in this quadrant, it's doing positive electrical power, negative electrical power, positive, negative. And these are the kind of relative signs that you would get for each of these terms. So this would say if we were doing actual Kirchhoff's voltage law, they would sum to 0. This would have a negative sign and be on that side. You know that from the direction of the current, and the voltage drops across each element. In negative power, torque and velocity are in opposite directions, and in positive power, they're in the same direction. And this is just vocabulary. Okay, so this is the negative power version. Same exact concept. The only thing that changed was these terms, because those are dependent on the sign of the current, which is dependent on the direction of the torque. So in both of those, we switched the direction of the torque, which made them oppose, which made it negative power. Cool? Any questions on this? Okay. All right. So now this kind of brought us to mathematical modeling. We did these kind of 2 blocks of this pipeline, modeling transmissions, modeling electric motors, and now we want to actually investigate this particular task of building a ballbot, and we want to get here. We want to get the current and voltage required by this ballbot, so we know, is our motor spec'd correctly or our transmission ratio spec'd correctly? Once we do that, which is kind of the end of this lecture or maybe some of Thursday's lecture, we'll come back and do the thermal properties, and that'll sort of round out this pipeline. This part of the class it's not super clear to me how much mechanics everyone has seen, so help me like teach this effectively. So I think you guys might be on many different levels, coming from many different backgrounds and even years. So just kind of help me do that, right? So we're gonna stop here. We're gonna begin to model a simplified ballbot. Then we'll return to thermal analysis. And again, these procedures are general. So like think of this as a framework that you can apply in any sort of project going forwards. We're going to begin with Newton's second law, F equals ma, or some torques equals J theta dot. And in this class, we're kind of like basically mostly around the torque equation, but we do have some of the force equations as well. Before we can actually model this, we need an understanding of the forces, properties, and desired motion. Okay. We're going to talk about our task of our planar modeling of a ballbot. What we're going to do in this is model the mechanics of this system, prescribe a motion to that system, and get the required torque. This analysis is acausal. What does that mean? We're going from motion to the required torques. So you know what acausal means? Or causal? You've taken a linear systems class, they would probably talk about it. Causal means that the dynamics of the system only pertain to time in the past. So it doesn't require knowledge of the future to predict the mechanics. Acausal means that it does. This analysis is acausal. The reason it's acausal is because we're using derivatives. We're taking discrete derivatives, which is, in this world of high performance computing and really fast sample rates, it's an okay way to model, but it isn't the same as forward modeling, which would use something like an ODE solver like Simulink. That would be we actually have the forward version of this, which we can share with you. It's a Simulink model. It's very complicated. It's harder. So that's why we aren't going through that. We're doing the inverse model. And the inverse model is what we typically use to design robots anyways. But it does have this constraint that it requires knowledge of the future, meaning you have to be able to take a derivative. Yeah.
I was just wondering, is this ballbot sort of like a parallel robot in a sense, and that makes the inverse easier, or?
Sort of like a parallel robot in what sense? In its actuation?
Yeah, because like the motor is like all like act on the ball simultaneously.
Yeah, you could think of that, but I wouldn't say that that's why we're doing causal versus acausal. This is a kind of a decision that's made to make it easier to do this analysis. We could do the causal path, it would just be more sophisticated. And you guys probably are less familiar with Simulink than you are with MATLAB scripting, correct? So the Simulink model is intense. Okay, so it's acausal. It uses derivatives. Okay, so we want to talk about these major components. What we're going to do is model the ballbot in a single plane as a single wheel with a mass. So our ballbot looks something like what's in the sort of CAD background here. We're going to model it as a basketball with a wheel sitting on top and has a mass attached. attached to it at some distance. So very different than our three-dimensional version. How will those differences manifest in our analysis? What will be different about this? So let's say we do this analysis, but we're using it to spec the kind of 3D version with 3 motors. What differences would there be? There's one kind of major difference. Yeah.
The ability to like fall out of the page, I guess. Like
In like the kind of single plane version, there's no possibility for that. It's not kind of included in the model. Think about like the effort required by this green wheel compared to the effort required by those 3 wheels. Yeah.
Friction?
There could still be friction. The thing I'm trying to get at, which is like a little bit challenging, is this system has 3 motors and it has basically 2 planes of operation. We're looking at 1 plane. So we're going to distribute essentially this torque amongst 2 to 3 motors. So this torque will be greater than the torque that we need. So we could consider it as a conservative estimate. Because there's only, if you think, let's say now we combine this planar model with another planar model, that's pretty close to a 3D model. Now we have 2 planar models, but it only has 2 wheels, whereas this system has 3 wheels. So we're going to take whatever torque is required by these 2 wheels and actually distribute them over 3 wheels. So the torque ends up being greater in this approach. Differences: more torque will be required because there's 1 wheel instead of 2 or 3, depending on how you think of it. So I would say this serves as a conservative estimate. So we can kind of like, if we base our designs kind of on this analysis, we'll be safe. Serves as a conservative estimate of torque. Does that make sense? The conservative estimate part? Yeah.
So that just saying that like this is gonna give us like an upper bound?
Yes,
Okay.
that's exactly what I mean. This is going to kind of provide an upper bound to us. So if we design our system to handle this model, then it will definitely be able to handle the 3-wheel version. So this image that we're looking at is the XZ plane. What would be different if we were modeling the YZ plane? So that's the other plane. So we have the XY plane is flat parallel to the ground. We have an XZ plane and the YZ plane, which are the planes of motion. What would be different if we analyze the other plane?
Couldn't it technically be the same if you like, I mean, it's just like looking at it from like a different side.
Yeah, it's the same. Nothing would be different. Yeah, so this system is identical in these planes. So that's helpful. When we model one plane, it won't be that difficult to go up to a 2-plane model, which is very close to the 3D model, because these planes are the same. Okay. So now that we're kind of getting closer to modeling this, we can think about that these systems have properties, physical properties, and we want to know what those are. So these components, they have physical properties, values we're going to list. When you're modeling, you might have to do this kind of thing. You might have to find these properties. Where can you find them? How can you get them? So we're looking at properties like this.
I think for the moment of inertial ones, you could try using the CAD software as a rough estimate.
Definitely. As we'll go over, so not next lab, but the lab after that, we're gonna start doing SolidWorks. So next week. Next week we'll start doing SolidWorks. SolidWorks, you can put in SolidWorks or solid modeling software, you can prescribe materials to things. They have geometry, it will calculate all of these properties for you, mass, moment of inertia, those things. So CAD software is a great one. Also like direct measurement. So getting out a caliper or a scale and just measuring it yourself. Also data sheets, websites. We kind of get this information any way we can. And the fidelity of this model does depend on the kind of ability you have to know these properties. So there's a whole field of engineering that goes into identifying properties like this. In this class, most of it we can read off of the data sheet, which is convenient. Okay, so let's go through some of these. I'm gonna kind of list what we have used for these. These values may be eventually a little bit different than the values that you guys have, but they'll be close. For modeling purposes, they'll be good. Our L is about 0.23 meters. That's the distance to the center of mass. We're talking about so body and chassis is blue, the wheel's gonna be green, the ball is red. So L is 0.23 meters, the mass of the chassis. Ours is 1.71 kilograms, so it's kind of heavy. Its inertia and the X and Y planes are identical. We'll just say it's 0.01 kilogram meter squared. Its inertia in the Z plane, it's maybe a little bit different, but that won't actually come into play. .017 kilogram meter squared. The wheel that we're using has a mass of 290 kilograms, or 290 grams. Its radius, 0.1 meters. And its inertia, 0.001 kilogram meter squared. Yeah.
So when you say these are like the properties of the wheel isn't a part of the actual robot because it has 3 different wheels. This is just the wheel we're using to model.
No, this is the actual wheel. So the wheel, we're actually modeling this wheel here.
Oh, okay.
Yeah. But you could, that doesn't necessarily have to be true. You could model it as a different wheel, then it would add some differences in the current and voltage. And then the balls is our basketball. It has a mass of 620 grams. A radius of 0.12 meters, and an inertia of 0.004 kilogram meters squared. Here, zoom. Okay, so this would be kind of as you're beginning to start your modeling process, you'll end up with a bunch of parameters that describe the physics or mass and inertia of your system. You have to keep track of those. And so we kept track of them, and I'm just kind of starting here by just listing them for you. Yeah.
I just want to say confirm, what is L? Is it the distance to the center of the wheel or like half of the
It's the distance to, we'll come back to this. It's the distance to the center of mass.
Okay.
Like a representation of the center of mass.
Gotcha, okay.
Okay. So we have our we're beginning to kind of have our system defined. Now we need to talk about its motion and how to describe its motion. We need to define parameters that describe the motion. And our planes here are identical. This is the way that we'll talk about the motion of the ballbot. So these variables are gonna come up a ton. So I'll try to like refer to them both in their kind of Greek form, but also in their actual physical form. But these variables are variables we're gonna talk about a lot. So body and chassis motion, it's defined by a lean angle, we call theta. So that's the lean of the body and the chassis around the ballbot. That variable is theta. We also have motion of the wheel. So the wheel is rotating. It has a description. Its motion is phi. That's where phi came up in our previous analyses. This should be phi. I mean, psi. So I'll like change that. Ball motion. Same thing, we have to understand the rotation of the ball and its translation in the planes. So x of k is its linear translation, rotation of the ball is phi. I'm gonna say. Those are psi's. So we have theta, phi. This is around wheel motion around the ball, so theta. And then we have translation or motion of the body of the ball in the planes, so moving forwards or backwards. And then we have its rotation, phi. Good? Okay. How many degrees of freedom does this system have? Anybody know? 4. Do you know what they are?
I just read it off the screen, but I can try.
Oh, it says it on the screen. I was impressed. Do you want to give a stab at what they are?
Sure. So there's
give one or two.
rotational freedom. I guess it depends on how you defined it, but I would say like the z direction of just like how that rotates. And then you have translation motion in I guess all 3 directions if you
In this plane, it only moves forwards, so there's no elevation change, so it just moves forwards. So we have x of k, so we'll say forward motion of the ball. We have theta, which was our lean angle. We have phi, which was the rotation of the ball. We have psi, which is the rotation of the wheels. Oh man, looks like there's like a box here that shouldn't be here. These are our 4 degrees of freedom. There are 2 constraints. We have 2 constraints. One constraint is that the wheels don't slip. So the way that I think of that is going to be that xk, basketball does not slip at BC. So right here, basketball does not slip there. So we know that x of k is going to be rk times phi. The other constraint is a tangential velocity constraint, which is this guy. This is that BC. Sorry, these blocks are there. I don't know how those got there, but that's a bummer. So we have no slip condition. We have a tangential velocity constraint, which says at this point, B and C, it does have to have the same speed. That's a little more complicated because of the fact that both, there's a contact point at B and C is rotating with theta. So that description is a little bit more complicated, which is why it maybe like doesn't look as intuitive as the x of k constraint. So now we have 2 remaining degrees of freedom. We have 4 degrees of freedom, 2 constraints, we have 2 remaining degrees of freedom. In our approach, we're doing the inverse modeling. We have theta and x of k for inverse modeling. If we were forward modeling with Simulink, we would use different degrees of freedom. We would use theta and psi. For forward modeling. So our system has 4 degrees of freedom, reduces to 2. That means in this analysis, we need to have motion profiles for these degrees of freedom. So now we need to create motion. And what we're going to get is the torque required to do that motion. So whatever we give it in terms of these motion profiles, it's going to return to us the torque required to do that. So picking those motion profiles is important because we're benchmarking everything on what we get for this specific motion profile. Okay, so we've talked about the planar ballbot, kind of some vocabulary, some different coefficients that exist. And we talked about its degrees of freedom. We talked about its 4 degrees of freedom reduced to 2, and we're going to prescribe motion for these 2 degrees of freedom. This is sort of the last step before we can actually model it, do free body diagrams, and then calculate. So if we want to prescribe motion to this, we want to prescribe motion to the 2 remaining degrees of freedom. Then we give it xk. So what do we want the system to actually do in terms of xk? If we want to predict the torque, we need to generate a motion profile. Who picks this motion profile? We choose this. When speccing, so we're making a decision here by selecting a motion profile. How long do we want it to take? What does it do? In this motion profile, I've created a velocity trajectory. It starts out at rest. At 2.5 seconds, it begins to increase at a constant velocity, or a constant increase to a constant velocity at 6 seconds. I then took that profile and smoothed it, so it doesn't have sharp corners. Taking derivatives and sharp corners are not good paired together. So the red line is the smoothed version of it. That's what we're going to say is our input. What we specified is what is the maximum velocity we want the system to be able to reach. So imagine you're driving this ballbot, there's a ballbot whizzing across the floor. How fast should it be able to go? And this matters a lot. Like this defines a lot about what's gonna happen. We're choosing it for 1 meter per second as like a top speed, which is pretty fast, I'd say. So we have like ambitious top speed of 1 meter per second. And then the question would be, how long do we want it to take to get up to 1 meter per second? I kind of chose 3.5 seconds, which seems reasonable, doesn't seem too fast, seems like a reasonable time for it to get up to that. If we make it, obviously if we make it take longer, that's gonna be a lower acceleration, it's gonna be easier for the motor and actuator to do it. If we try to make it faster, it's gonna be more acceleration, that's gonna be harder, it's gonna produce more torque, more current. So we wanna spec these based on what we want it to actually do. I think 1 meter per second seems about right. So final velocity is 1 meter per second. Ramp duration, 3.5 seconds. That creates, in a resulting acceleration, looks like this. So we want it to accelerate at something like 0.25 meters per second per second. What will this say about voltage and current? Just based on the fact that you wanted to do this, you have some ideas about what the general shapes of the voltage and current profiles would be? Yeah.
Can we like plug this into the motor model that we have?
You can, that's actually what we're gonna do. But just before we get to that, what I would love for you guys to be able to do is sort of like gut check. Hey, I see this, I sort of already know generally like what the shapes of the response will be. And the answer, like the way I would think of it is, the answers are they're gonna be somewhat similar to these shapes. So the acceleration is gonna be like somewhat similar to the current torque. So we should look at acceleration is gonna be similar to torque. It's gonna be similar to current. Velocity is gonna be similar to voltage. So we should see, if we kind of did this right, we should see a voltage profile that generally does something like this, and a torque profile that generally does something like this. We could go one level deeper and sort of like talk about how these would change, but maybe we'll come back to that. It's a little much. Okay, so we created a motion profile that's based on our task. What about our other degree of freedom? We're determining motion profiles to understand actuator demands. We also need to provide information on the other degree of freedom, theta, which is lean angle. We gave it a trajectory to follow, to roll forwards. We haven't talked about like whether it would lean. Do you think it will lean, or is there some relationship? Do we have some relationship between the way it moves and how it leans? Yeah.
It feels like the two are sort of connected. Like you would need to lean in a direction in order to like accelerate in that direction.
Yes.
So I was a bit confused why there are like two separate degrees of freedom.
So okay, this is a great question. It's a little bit nuanced. Everything you said is correct. If we want to do this inverse analysis to get the current and voltage, we have to have a relationship for all the degrees of freedom. This relationship is constrained by the physics. So here, the inverse modeling breaks down a little bit. So we can get close. Basically, we can kind of like do this, we can choose the lean angle such that it is close to what we would expect, and we can use that to spec current and voltage. Can we say we are confident that it's 100% right? No, because these are connected through the physics. If it's leaning, its center of mass, its moment arm will create the net torque that's accelerating it. So there's an inherent link between its lean and its acceleration, but that link is only able to be solved implicitly if you do the forward model. The forward model would follow all of those. The inverse model will be close, or I can't say that it's ideal, but it does allow us to quickly and easily get to the required current and voltage. That's why we're doing it. Okay. So we need to choose something for it to, we need to choose a profile for it to lean, and we want that to be somewhat physically realizable, somewhat to make sense. So how about, this is how we chose to do this. How about we have it lean something that's proportional to the acceleration. We know the acceleration is really going to be somewhat proportional to torque. So we want the lean angle to kind of also be proportional to acceleration. So similarly, we choose this. How far do we want it to be able to lean? There's also other constraints in that, like if a ballbot leans over sufficiently, its wheels lose contact. And then if the model breaks down, it can't actually actuate anymore. But we're going to stay away from leaning that far. So we know this should lean with like torque. So our approach is to scale the linear acceleration to an acceptable trajectory. What do I mean by acceptable? Well, when we know lean angle is constrained, we know it can only lean so far before the ball loses contact, and then it sort of falls apart. So lean angle is physically constrained from the wheels losing contact. Let's use approximately 4 degrees. That's about all we have to work with. If it leans more than about 4 degrees, it can't really recover. So we kind of know we want this lean angle about 4 degrees as an acceptable value. That's 0.07 radians. So what we end up with is a lean angle trajectory that looks like this. Follows acceleration, so now it's going to lean as it accelerates, and then when it reaches constant velocity, it's going to lean back, then be back to upright. So this would be like perfect ball-bot behavior. Our ball-bots will not actually do this. It'll be much noisier, shaking around. But now we have our trajectories. We have our input, xk, and now we have our lean angle theta. Trajectories that seem to make sense. Okay, I think we're going to get through this, which is good. Now I want to do the free body diagram for this. Let's go through this slowly. So now we have some trajectories. We understand the process. We can model the motor, but how do we get the torque? In order to get the actual torque, we have to physically model the ballbot, which we're going to do by going through its mechanics in one plane. So this guy, that's our x of k. Okay, so all I've done here is I've separated our components. Basketball, wheel, mass, chassis mass. Our basketball has a few forces that act on it. It has the force of the contact point with the ground. So this is FK2, this is FK3. I've broken it into two components. We have its force actually acting gravity, and then we have the contact force with the wheel. Also two components, FW3, FW2. If we look on the wheel side, we have the equal and opposite versions of that. We have FW3, FW2, so mass is FW1. Then we have the forces applied by the chassis. FA3. FA2. And this is the point where it contacts the wheel. And then we have Tx acting on that wheel. And Tx acting on the chassis. So all we did was break our system up, determine the forces acting at each interface, put them into components, and give them names. So that's kind of what's happened here. So we have a bunch of forces acting on this. Which forces do we care about? So what we care about, well, remember, what are we trying to get right now?
Motor torque.
Motor torque. Where's the motor in this system?
On the wheel, so TX.
Acting on the wheel. So what we want is Tx. So what forces do we need to actually compute that? FW2. That's going to be the force acting at the interface between the wheel and the ball, and it has to move around all the different mass components. Constraints, these are the constraints we talked about. No slip, tangential velocity constraint, also no slip. We can get the ball velocity by numerically differentiating xk, which we have defined. We know rk, so now we have phi dot. We have this expression for FW2. What I'm not going to do is kind of go through the mechanics to get that because it takes a really long time. So I don't think it's, at this point, I don't think it's required for this. This level of like dynamics that I don't think is super helpful to include in this class. So my current thought is just provide this as is. Worked out. So if you guys are building a robot, you may or may not be building one like this mechanically complex. Most likely not. Like usually, this is one of the more mechanically complex robots that I've worked on. So my hope is that like you guys wouldn't, if we spend the time to go through how to do this, which is kind of a upper level dynamics exercise, you wouldn't get the benefit of that. Like you wouldn't, that time wouldn't be worth like your time for the knowledge you're getting for use of this in the future. So my thought is to provide it to you like this, but also like let me know that, how you're thinking about that. If you guys want to know the details, it's definitely possible for us to go through it. We'll probably take a class. Okay, so you do some free body diagram or mechanical analysis of your system. That will generally tell you the equations at play. Usually they're not this complicated. This system is a little more complicated, so we have kind of an intense set of equations that govern the mechanics, but if you were building, for example, lots of other types of robots, it may not be this intense. But I feel like it's good for you guys to see this either way. And if you've taken your upper level dynamics classes in the ME department, for example, you would be able to do this. Okay. This is kind of like, this is pretty much where I wanted to end. I have one more slide after this. So we're doing great. Okay. We have our description, we have our input, which is our profiles, motion profiles. We have our description of the mechanics that tells us torque. Now what we want to do is plug all this in, calculate current and voltage. These equations come from free body diagrams. These equations are your constraints. Got by common sense physics. That balls, they can't slip when they roll. And now we have the expressions for current and voltage. This is current, voltage. What is this term? Now we're going to kind of go through these terms. What is that term?
Through the transmission.
Say it again.
Torque, like with the transmission ratio.
Yeah, so this is the torque, the output torque, Tx.
So it's the input torque.
Yeah, this would be the kind of output transmission, which we call the input to our pipeline, divided by n and eta. So that tells us this is the torque required by the motor to do the work kind of at the output, to actually like do the task, move the ballbot. What's Jn phi double dot? What is that? Torque required to accelerate the rotor's inertia. It's this guy. Torque required to overcome the viscous loss, the damping, the friction inside the motor. Then we divide everything by kT and it gives us the current. So all we had to do is kind of get these correct, understand our coefficients, and we get the current. Similarly, so we do these. So this was output torque to move ball and mass. Torque to accelerate motor. Torque lost to friction. And again, kind of what this is saying is we want the current to be responsible for providing a torque that does all three of those things. What do we have here? We're going to do the same thing with voltage. What is this? Voltage drop across.
Internal resistance.
Yes. What's this? KT and psi dot? What?
Voltage across the motor.
This is the back EMF, which I think is what you're saying. But we'll call, to be more specific, we'll say back EMF voltage. So that's the voltage induced by the motor spinning. And our last one is our voltage drop across the inductor. Why does it have a resistance and inductance?
That's the way the motor's built.
Yeah, it's a giant coil of copper. Copper, like wire, has impurities and resistance. It is literally wound around an iron core. It is an inductor. Okay, so we have all these terms. One quick thing that I want to mention, at the risk of confusing you, but my fear is you'll notice this later when you review the notes if you haven't noticed it already, is in these equations I included n. But in the previous equations we were modeling the motor, there wasn't an n. It didn't include the transmission ratio, it just was about psi. And the reason for that is both the document, the thesis, which is a reference for you, and our kind of internal work, we don't have a variable for the motor's rotation. We have a lot of variables for rotations, but not the motor's rotation. What we have is a variable for the wheel's rotation, psi. So when I was doing that original analysis, I was sort of acting like psi was the velocity or psi was the position, but that's actually the position on the other side of the transmission. We don't have a variable for that, so now it's every time you see it, it's got n attached to it, because now we're on the motor side of it. So all of those you'll see kind of in this, and then also in the MATLAB code. We've just described everything at the motor without actually calling it a variable. It's always n times psi of something, psi dot, something like that. Does that make sense? Okay, let me know if that's confusing. Okay. This is what we get. So here again, we have our equations that we used, current and voltage, constraints, force. We compute that, run it through, we get profiles that look like this. Red is our current, blue is our voltage. Somebody talk me through the shapes that you see. And we were talking about the shapes. You know, the velocity was a ramp function. What do you see here? What is this value? So where does it come from? This is the voltage. Yeah.
That's when it reaches its maximum speed.
And so what would this entirely be, or like almost entirely be what? What term in the motor's voltage equation? Back EMF. So at this point it's spinning fast. It's ramped up to a constant velocity. And it's, yeah, at this point, I should have put the ramp function, but at this point it's just spinning really fast under no acceleration. It's reached the plateau of the ramp. So what we're seeing here mostly is not entirely this, but mostly that's the back EMF generated from how fast the motor is going. What is this? What is this? Not these little bumps, but mostly that shape. Yeah.
Overcoming the torque to actually start spinning.
That's the torque to dry the inertias. This is the back EMF. What is this?
Is that the torque to overcome the resistance, the internal like damping?
That is. It is the current or torque to fight viscous loss. So then at that point it's not accelerating anymore, so there's no more external torques essentially on it. So all it's doing right there is maintaining a constant velocity and fighting the resistance, the viscous resistance in the motor. Here's a challenge question. What is this? Yeah.
It is like the current and resistance term that comes from the current graph above. I think so it kind of looks like the current graph like slanted and smashed on top of the voltage with
Yes.
that part.
So there's this shaded part is coming from a term. I think you're saying the term. That is coming from, so the reason why it doesn't look like a straight ramp, which would be like just almost entirely back EMF, we see an increase there, and that increase looks like it's connected to the current. That's the I times R term. So we're seeing there the increase in the voltage required because we have a drop across I times R, which comes from a high current that's going through it. So when this comes back down, we see that come back down too. So when you kind of look at these curves, there's a ton of information you can kind of get out of them, both as a sanity check, but also as a way to inspect these systems and understand their requirements. So this system would take about 1 amp to do that accelerating. That's pretty much the continuous current limit of the drives that we're going to use. So this system has been spec'd, meaning when we went through the motors that were available and the transmission ratios that were available and found something that converged, that gave us this. Next class, I'm gonna give you that MATLAB script. We're gonna kind of do that together. I'll try to create an exercise where you use that MATLAB script and maybe make some changes. I can show you where the motor parameters came from. But next time we're gonna kind of dive into this. And then from there, I don't know what we're gonna do. Well, I think so that's all I think we're gonna cover today. Let me see if there's anything else we wanted to say about this. These little bumps, I haven't quite figured out what they are. I think they come from the numerical differentiation that I'm doing. If you'll notice, they are the transition points of the original non-smoothed ramp function. So like that's kind of start and stop of how it got smoothed. So, but I don't think it really matters yet.
So did you generate these graphs from measuring the actual voltage and current of it running, or did you create these in MATLAB using those equations?
I created with MATLAB using those equations. The hope would be if we actually did measure it from the real system, that it would give us something similar to this. But yeah, this was all done, generally, this is all done before anything's built, so that you kind of know what to build. Now we know what transmission ratio, what motor, and we can start building our structures. Okay, come to office hours if you guys want to chat. I'm going to post homework today. Take a look at the due date, see if you're comfortable with it. Pick up here on Thursday, see you tomorrow at lab. Turn your laptops, create a GitHub account.